In class 11th, you have learnt that the p block elements are placed in groups 13 to 18 of the periodic table. Their valence shell electronic configuration is ns2np 1 to 6, except helium, which has 1s2 configurations. The properties of p block element, like that of others, are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy, and electronegativity. The absence of d orbitals in second period and presence of d and or f orbitals in the heavier elements starting from the third period onwards have significant effects on the properties of elements. In addition, the presence of all the three types of elements, metals, non-metals, and metalloids, bring the diversification in chemistry of these elements. Having learned the chemistry of elements of groups 13 and 14 of the p block of the periodic table in class 11th, you will learn the chemistry of the elements of subsequent groups in this unit. Group 15 includes nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloidic character. Nitrogen and phosphorus are non-metals, arsenic and antimony are metalloids, and bismuth is a typical metal. Molecular nitrogen comprises 78% by volume of the atmosphere. In the Earth's crust, it occurs at sodium nitrate, that is NaNO3, called chill saltpeter, and potassium nitrate, Indian saltpeter. It is found in form of proteins in plants and animals. Phosphorus occurs in minerals of apatite family. Ca9PO4 6, CaX2, where X can be fluorine, chlorine, or OH. Example, fluorapatite, Ca9PO4 6 CaF2, which are the main components of phosphate rocks. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as in living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found mainly as sulfide minerals. The important atomic and physical properties of this group elements, along with their electronic configurations, are given in table 7.1. Trends of some atomic, physical, and chemical properties of the group are discussed below. Electronic configuration. The valence shell electronic configurations of these elements is ns2np3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Atomic and ionic radii. Covalent and ionic in a particular state radii increase its size down the group. There is considerable increase in covalent radius from N to P. However, from arsenic to bismuth, only a small increase in covalent radius is observed. This is due to presence of completely filled d and or f orbitals in heavier numbers. Ionization enthalpy. Ionization enthalpy decreases down the group due to gradual increase in atomic size because of the extra stable half-filled p orbitals electronic configuration and smaller size. The ionization enthalpy of group 15 elements is much greater than that of group 14 elements in the corresponding periods. Electronegativity. The electronegativity value in general decreases down the group with increase in atomic size. However, amongst the heavier elements, the difference is not that pronounced. Physical properties. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas, while all others are solids. Metallic character increases down the group. Nitrogen and phosphorus are non-metals. Arsenic and antimony are metalloids, and bismuth is a metal. This is due to decrease in ionization enthalpy and increase in atomic size. The boiling points in general increase from top to the bottom in the group, but melting point increases up to arsenic and then decreases up to bismuth. Except nitrogen, all the elements show allotropy. Chemical properties, oxidation states and trends in chemical reactivity. The common oxidation states of these elements are -3, +3 and +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. In fact, last member of the group, bismuth, hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreases down the group. Only well characterized bismuth 5 compound is BiF5. The stability of +5 oxidation state decreases and that of +3 increases due to an inert pair effect down the group. Nitrogen exhibits +1, +2, +4 oxidation states also when it reacts with oxygen. Phosphorus also shows +1 and +4 oxidation states in some oxoacids. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. For example, 3HNO2 gives HNO3 plus H2O plus 2NO. Similarly, in case of phosphorus, nearly all intermediate oxidation states disproportionate into +5 and -3 both in alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth become increasingly stable with respect to disproportionation. Nitrogen is restricted to a maximum covalency of 4 since only 4 1s and 3p orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell which can be used for bonding covalency and hence expand their covalence as in PF6-. Anomalous properties of nitrogen. Nitrogen differs from the rest of the members of this group due to its smaller size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and with other elements having small size and high electronegativity. Example: carbon, oxygen. Heavier elements of this group do not form p-pi bonds as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Thus, nitrogen exists as a diatomic molecule with a triple bond 1s and 2p between two atoms. Consequently, its bond enthalpy 94.4 kJ per mole is very high. On the contrary, phosphorus, arsenic, and antimony form single bonds spp, ss, and sbsb, while bismuth forms metallic bonds in elemental state. However, the single NN bond is weaker than single PP bond because of high interelectronic repulsion of non-bonding electrons owing to the smaller bond length. As a result, the catenation tendency is weaker in nitrogen. Another fact which affects the chemistry of nitrogen is absence of d orbitals in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form d-pi-p-pi bond as the heavier elements can. Example: R3p double bond O or R3p double bond CH2, where R is any alkyl group. Phosphorus and arsenic can form d-pi bond also with transition metals when their compounds like P CH2H5 whole thrice and As C6H5 whole thrice act as ligands. Reactivity towards hydrogen. All the elements of group 15 form hydrides of the type EH3, where E is equal to nitrogen, phosphorus, arsenic, Sb, or bismuth. Some of the properties of these hydrides are given in the table 7.2. The hydrides show regular gradation in their properties. The stability of hydrides decreases from NH3 to BiH3, which can be observed from their bond dissociation enthalpy. Consequently, the reducing character of the hydrides increases. Ammonia is a mild reducing agent, while BiH3 is the strongest reducing agent amongst all the hydrides. Basicity also decreases in the order NH3 greater than PH3 greater than ASH3 greater than SBH3, which is greater than or equal to BiH3. Reactivity towards oxygen. All these elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than the oxide of the lower oxidation state. Their acidic character decreases down the group. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic. That of arsenic and antimony amphoteric, and those of bismuth is predominantly basic. Reactivity towards halogens. These elements react to form two series of halides, EX3 and EX5. Nitrogen does not form pentahalide due to non-availability of the d orbitals in its valence shell. Pentahalides are more covalent than trihalides. All the trihalides of these elements except those of nitrogen are stable. In case of nitrogen, only NF3 is known to be stable. Trihalides except BIF3 are predominantly covalent in nature. Reactivity towards metals. All these elements react with metals to form their binary compounds exhibiting -3 oxidation state, such as Ca3N2 calcium nitride, Ca3P2 calcium phosphide, Na3As2 sodium arsenide, Zn3Sb2 zinc antimonide, and Mg3Bi2 magnesium bismuthide. Preparation of dinitrogen. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid dinitrogen, boiling point 77.2 Kelvin, distills out first, leaving behind liquid oxygen, boiling point 90 Kelvin. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrate, NH4Cl aqueous plus NaNO2 aqueous gives N2 gas plus 2H2O liquid plus NaCl aqueous. Small amounts of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by thermal decomposition of ammonium dichromate. Very pure nitrogen can be obtained by thermal decomposition of sodium or barium azide. Properties of dinitrogen. Dinitrogen is a colorless, odorless, tasteless, and non-toxic gas. It has two stable isotopes, 14N and 15N. It has a very low solubility in water, 23.2 cm³ per liter of water at 273 Kelvin and 1 bar pressure, and low freezing and boiling points. Dinitrogen is rather inert at room temperature because of the high bond enthalpy of N triple bond N bond. Reactivity, however, increases rapidly with rise in temperature. At higher temperature, it directly combines with some metals to form predominantly ionic nitrides, and with some non-metals covalent nitrides. It combines with hydrogen at about 773 Kelvin in presence of a catalyst, Haber's process, to form ammonia. Dinitrogen combines with dioxygen only at very high temperature at about 200 Kelvin to form nitric oxide, NO.